sixth and final round of this javelin competition. He really is getting confident and hammers that one out. Oh, look at that. That was a sensational throw. That's got to be over the 90-meter mark. Have a look at this. He wallops it. He really is strong.
Okay, today we're going to be looking at a very classic problem. And the problem, or the question, is if I throw this ball or throw any projectile, what angle should I throw it at for it to reach a maximum horizontal distance? That's the problem we're going to try to answer today. So let's go ahead and look right at it.
Specialize in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.
Okay, so this problem is going to deal fundamentally with calculus. It's going to utilize something we call optimization, but it's also going to require, some pre-cal, parametric functions, trig, vectors, and things such as that. So let's outline a sketch of the situation. So what we want to do is we want to throw the ball or some projectile at some given initial velocity. And so I'm going to represent that initial velocity with a vector. And we're going to call that initial velocity V naught. And the question we want to ask is, at what angle theta should we throw this ball for it to reach its maximum horizontal distance? Now, when we throw this projectile, its path is going to be that of a parabola. So it's going to travel somewhat like that, starting here and hitting here. And what we want to figure out is what is this maximum distance here. All right, so the position of a projectile thrown such as this at some initial velocity of V naught and some angle theta has well-established equations. So I'm going to use a parametric equation, one equation for the horizontal position and another equation for the vertical position. So the horizontal position, and I'll describe it as x, it's it's V naught cosine theta times t. And the vertical position, which I'll call y, is -5 t squared plus V naught sine theta times t, pardon my handwriting, plus the initial height. For the sake of this problem, I'm going to make the initial height 0. Just makes the math a little bit easier to make the initial height 0. Now, these are well-known functions for the horizontal and vertical position, respectively. Now, just a little bit of background on how we get those. These two formulas represent distance primarily, and you know that speed is distance over time, so therefore distance is speed times time. And if we go back to this vector projection here, and if we call this, so this is the velocity vector, and it has a horizontal component which we can call VH, and a vertical component which we can call VV. And if we want to solve for VH, for instance, knowing that we know V naught, this is adjacent and hypotenuse, so cosine theta would be VH over V naught, which means that VH would be V naught times cosine theta. So the horizontal velocity is V naught cosine theta. And again, distance is simply velocity times time. And you can see here, there's the horizontal velocity times the time. And similarly with the vertical position, same thing here. V sub V is opposite, and I know V naught, that's hypotenuse. So we would say that sine theta is v sub v over v naught, which in 2 would imply that v sub v, let me just write it up here, v sub v is v naught sine theta. And so the vertical position is the velocity times the time. And, you know, you also take into account, because it's vertical position, the initial height, which in this case we're saying is 0. And this negative 5t squared, where that comes from, is due to acceleration due to gravity. So there's really nothing, there's not a horizontal force working against or with the horizontal velocity if we neglect air resistance. But there is a force working against the vertical velocity. And that's why we have this negative 5t squared added to the vertical position. So that's kind of a little background on how we get those problems. Now, in an optimization problem, you have to identify the equation that you want to maximize. And here I'm trying to see what angle theta would give me the farthest horizontal distance. So I want to maximize the horizontal position. So let me rewrite, since these were a little bit sloppy, and I really apologize. I'm just going to rewrite the x equation and the y equation, try to express those guys in a little more neat fashion, and then kind of dissect what to do next. So I'm just rewriting a horizontal position function where x is v naught cosine theta times t, and I'm rewriting the vertical position function where y is negative 5t squared plus v naught sine theta times t. All right. So this is our primary equation. This is the guy we're trying to maximize. And we're trying to maximize it based off theta. I'm trying to find the value of theta that will give me the furthest horizontal distance. There's one problem, and the problem is that this function has two variables. It has theta and t. V naught is going to be a constant. It's not going to vary, but theta and t can vary. So I have two variables. And so when that happens, what we try to do is rewrite the primary equation with respect to one variable. So meaning we want to find a way to represent t in terms of theta to do some type of substitution. So that t term turns into a theta term. And generally we can utilize our secondary equation to do that. And this vertical position function is the secondary equation. Now, how can we choose the right substitution to make? Well, let me just redraw the simulation of the trajectory of this guy. All right, so there he is. Now, I want to find what angle theta to throw this guy where this distance is maximized. Now, I want to know the value of t right when it hits the ground at the very end. Because at the time t when it hits the ground at the very end, that's when it's traveled the full distance. So it makes sense to utilize that value for t. Well, when it hits the ground over here, t is, not t, y is 0, meaning when it hits the ground right here, its vertical position is 0. So if I simply take my vertical position function and set it equal to 0 and solve for t, that seems like the right move to make. Now, please understand that since we shot this guy at an initial height of 0, y is also going to be 0 at this point, and that's when t is 0. So that's not the point we want. So when we set this equal to 0, we're going to have two solutions. One of those solutions is going to be 0. Clearly, from the diagram, we can see that. But that's the starting point. We don't want that solution. So we want the non-zero solution, which will be this guy here. So we're going to get two solutions. One of them is going to be 0. That's not the one we're going to use. Obviously, we're going to use the non-zero solution. So this is the equation we're trying to solve. We're trying to solve for t here. Let me rewrite this guy on a separate sheet and simply solve it. So our equation is negative 5t squared plus v naught sine theta t equals 0. Now, there's a couple of ways we can solve it. Probably the easiest way to solve this guy is by factoring. If I factor out a t, I'll get t times negative 5t plus a v naught sine theta equals 0. And I have two factors here, and setting both of those factors equal to 0 solves the equation. Now, if I set this factor equal to 0, I get t equals 0. That's the solution I'm going to discard. So the real solution I want is setting this factor equal to 0 and solving for t. So negative 5t plus v naught sine theta equals 0. And then you'll get that t is v naught sine theta over 5. So when the projectile hits the ground after it's traveled the full distance, the value of t is v naught sine theta over 5. And so we'll take that value of t and we'll substitute it into the horizontal position function, therefore removing the parameter t and having a function just in terms of theta. And so just to remind you, the horizontal position function was v naught cosine theta times t. And so again, we're going to take this t and replace it with this t. And so what we're going to have is x is v naught cosine theta times v naught sine theta over 5. And what we'll get v naught squared over 5 times sine times cosine. All right, so let's write that. So our primary equation now, just in terms of theta, is that x is v naught squared over 5 times sine theta times cosine theta. All right, so now we have a good primary equation just in terms of the variable that we're trying to maximize, which is theta. And so what we'll do is we'll take the derivative of this particular guy and find any critical points we can find. And we'll plug the critical points and the endpoints of our implied domain into this function and see which one gives us the biggest value. And so before we do that, let's talk a little bit about the implied domain. And the implied domain is just the smallest and biggest value of theta to represent this particular problem. So if you think about it, the smallest value theta would be 0. The biggest value theta could be, for me to throw this ball and then not go backwards, would be 90. So our implied domain is 0 to 90, or 0 to pi over 2. All right, so that's our implied domain. So let's go ahead and take the derivative of this guy. Now, again, remember, v naught is simply a constant. So v naught squared over 5 is simply a constant. And there's going to be a little bit product rule on this particular derivative. So let's go ahead and do it. So I'm going to take the v naught squared 5 out like this. And then I'm going to do the product rule. So first thing I'll do is I'll take the derivative of sine, which is cosine, times cosine. That will give me cosine squared theta. And then plus, I'm not going to write the plus because when I take the derivative of cosine, it's going to give me a minus sign. So plus, and now I'll leave the sign alone and take the derivative of cosine, which is negative sine. And so that would be negative sine squared. So minus sine squared theta. And so this is, this is x prime. And so this is the derivative. And we'll set this guy equal to 0. And we'll try to determine any critical points we can find. Now, if we think about it, so our endpoints here are 0 and pi over 2, or 0 and 90. Now, sine of 0 is 0. That's going to make everything 0. Cosine of pi over 2 or 90 is 0. So that's going to make everything 0. So from the endpoints, this function equals 0. And it's, it's easy to think about. If I throw the ball at a 90-degree angle, it's going to go straight up and come straight down. So it's going to travel a horizontal distance of 0. And if I throw the ball at an angle of 0, I'm just throwing the ball at the ground. And when we're talking about the horizontal distance, we're not talking about the distance after it hits the ground and bounces. We're talking about the distance after it hits the ground. So it's easy to see that those two are going to give me 0. So then it makes sense to think that our answer is going to come from a critical point. All right, so let's find the critical points. Now, if you think about it, obviously for this whole thing that equals 0, the value of sine theta, of cosine theta and sine theta should be equal. And so you probably can think about that angle where sine theta equals cosine theta in quadrant 1 from 0 to pi over 2. And in fact, that angle is pi over 4 or 45 degrees. So you can kind of see that here. If that understanding, you can solve this real quickly. Another way of doing it, if you couldn't see that, but one would think that you would understand that on the first quadrant, sine and cosine are equal at pi over 4. But you can also, if you want, do a little substitution. And I can rewrite cosine squared theta as 1 minus sine squared theta. That's a Pythagorean identity. So I'm going to do that on a separate sheet. And so let me just rewrite the problem. And again, we've already established that the critical point is pi over 4. But I just want to illustrate, another way of finding that critical point if it's okay. So again, I'm going to rewrite, and we're saying it's equal to 0 and solving for theta. I'm going to rewrite cosine squared theta as 1 minus sine squared theta minus sine squared theta equals 0. I'll multiply both sides by 5 over v naught squared. Again, that's a constant, so it would cancel that out, and that would turn to 0. And then I would combine these two sine squared thetas, and I would have 1 minus 2 sine squared theta equals 0, which means that 2 times sine squared theta equals 1, or sine squared theta equals 1/2, which means that sine theta equals the square root of 1/2, which is 1 over the square root of 2, which can be thought of as the square root of 2 over 2. And again, in quadrant 1, the angle theta that gives you the square root of 2 over 2 is going to be pi over 4. All right, so again, another way of showing that the angle is pi over 4. And so we have already claimed that our critical point is going to be the answer. So it looks like the angle to throw the ball at would be pi over 4 or 45 degrees. But let's make sure, so let's plug it into the original function in terms of theta. And that would be this guy. So let's plug it in here. And all we're trying to do is get a value that's greater than 0 since the endpoints gave us 0. So let's try that. So our primary equation, and we plug it into the original equation, not the derivative. Our primary equation is x equals v naught squared over 5 times sine theta cosine theta. And you may be wondering, v naught is a constant, and you may be thinking, well, v naught could be different numbers, and it doesn't even matter because, v naught squared is going to be positive. So this is going to be some positive number. And so whatever it is, whatever the maximum number you get times a positive number is not going to change anything. So, v naught squared over 5 is really inconsequential to what we're doing here. So let's go ahead and plug pi over 4 in and see if we get a value that's greater than 0. And, when we plug in pi over 4, so v naught squared over 5, some positive number. Again, the sine, so this is x of pi over 4. The sine of pi over 4 is 1 over the square root of 2. The cosine of pi over 4 is 1 over the square root of 2. So we get 1/2. And indeed, that's a number that's greater than 0. And so indeed, pi over 4 will maximize the horizontal distance. So if you ever need to throw a projectile or a ball for any reason and you want it to reach its maximum horizontal distance, try to throw it at an angle of pi over 4 radians or 45 degrees. We'll see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.